Lecture 7. In this lecture we are going to talk about the derivatives. In standard calculus courses we all see what is derivative and learn different kind of techniques to compute and apply them. But in this part we are going to go a little bit deeper and try to understand the theory behind all these techniques. Suppose we have function f which is defined in some interval I, and suppose x0 and x are the points that belong to I. The usual difference quotient is given by fx minus fx0 over x minus x0, which is the slope. To see this, that this quotient is a slope. Suppose we have some function fx, and this is x, this is x0, fx0, then fx minus fx0 is this part, and this is x minus x0 minus x. Then the quotient is the slope of the chord determined by the point xfx and by the point x0 fx0. In other words, the quotient is the average rate of change of f on the interval with at endpoints at x and x0. The usual definition of the quotient is following. Suppose we have f which is defined on interval I, and let x0 be in I. The derivative of f at x0, which we denote by f prime x0, is defined as following. It's a limit when x goes to x0 x minus x0, provided that this limit exists. If f is differentiable at all points x that belongs to interval, we say that f is differentiable on interval I. Let's do one example. Suppose we have function fx is equal x squared, and suppose x0 belong to R. If x in R and x is not x0, now we want to find the derivative of this. Let's do the quotient. Then we use the simple algebra to simplify it. Which is equal x plus x0. Now if we take limit from both sides, we see that this is equal limit x goes to x0 x plus x0, which is equal to x0. We see that the derivative of x squared is 2x0. The interesting question is, what is the relationship between differentiability and continuity? Note that continuous function does not imply differentiability. However, differentiable functions are continuous. To see why continuous function continuity does not imply differentiability, let's consider the example of fx absolute of x. So the function is following. This is continuous function obviously, but it's not differentiable since in the point 0 the differential does not exist. Now we can prove the theorem which says, suppose f is defined in a neighborhood I of x0 if f is differentiable at x0, then f is continuous at x0. Now the proof. Note that to prove this, it suffices to show that limit of when x goes to x0 fx minus fx0 is equal 0 for x not equal x0. Then let's do the simple mathematical proof and multiply and divide this expression by x minus x0. Since x does not equal x0, we can do this. Now let's write this as a right hand side, and this is left hand side. And if we take limit from both sides, we get that limit of left hand side is equal limit of this expression times limit of this expression. This is from the product rule of limit. Then we know that limit of x0 fx minus, this is by definition is just the differential of at point x0, and x minus x0 is 0 when x goes to x0. Then we get that the limit of right hand side is equal 0, which we want to prove. So this theorem can be used in two ways. First way is, if we know that a function has a discontinuity at a point, then we know that there is no derivative. So if discontinuity point, no derivative. On the other hand, if we have been able to determine that a function is differentiable at a point, that we know that the function should be continuous there. So if we have with differentiable, then we know that it is continuous. Now let's talk about and prove some theorem about the combinations of differentiable functions. We know that functions can be combined algebraically by multiplying by constant, by addition or subtraction, and there is some calculus rule for computing the derivative for all these options. So the following theorem look on some of them. Suppose we have the function fg, which is defined on some interval I, and we assume that both function fg are differentiable at x0, which belongs to I. Then the theorem said that f plus g, differential of f plus g function is equal f prime x0 plus g prime x0. On the other hand, if we multiply function by constant, then it's equal constant times derivative. Third one says that the multiplication of the function, so this is called the product rule. And the quotient rule says given that gx0 is not 0. The first and second part of the theorem are defined by just using the definition. For example, for the first one, let's use definition of the differential, and we see that this is equal f plus g x0 minus f plus gx over x minus x0, which is equal fx0 minus fx plus gx0 minus gx, x0 and x minus x0, and we have limit here, which is equal each part separately, since limit of the sum is equal sum of the limits, then this is just f prime x0 plus g prime x0. The second is done the same way. Now let's prove the product rule. To prove the product rule, let's define a function which is equal f times g for all x in I. Then hx minus hx0 is equal fx times gx minus gx0 plus gx0 times fx minus fx0. Now we have that if we divide by x minus x0, where x does not equal x0, we get that this is equal now if we take the limit from both sides, the thing you notice is that this part is just the derivative of g prime x0 from the definition, and this part is derivative of f prime at point x0. Then we can write that limit of hx minus hx0 is equal fx times g prime x0 plus g x0 times f prime x0, which is needed to prove. Let's do a couple of more examples. Suppose we want to find the derivative of the linear function. So you can immediately apply the uh, definition here. You have different options to solve this. And you get that this is equal ax0 plus b minus ax minus b over x minus x0 minus 6, and this cancel out, so this is 8 times this is limit 8 times x0 minus x over x0 minus x. The limit of the constant is constant, and we prove a. The other thing you can do, you can take find the derivative of ax separately, derivative of the constant separately, and then use the sum rule of the derivatives to prove it. You know that the derivative of a constant is 0. To see that, again, you can use the theorem, the definition of the derivative, and see that this is just 0. Let's do one more interesting example and find the derivative of xn. So what we want to prove that this is equal n times x n minus 1. The proof is by induction. Remember that to have proof by induction, we need to do 3 steps. Now, we want to show that this holds for n is equal 1. When n is equal 1, we have that derivative is, from definition, is equal x 0 minus x over x0 minus x, which is equal 1, which is equal 1 times x 1 minus 1, which is 1. So this holds. Now we say, so this was the step 1. The step 2, we say suppose holds for n equal k. So we say that f prime x is equal n times x k times xk minus 1. And in step 3, we say we want to show that holds for n equal k plus 1. Now, we can use here the product rule, and we have that this xk plus 1 is equal xk plus kx. So from product rule, f prime x is equal derivative of xk. Let's define xk as gx. So this is derivative of gx times at point x0 times, and let's define x as ajax. So this is ajax plus gx 0 times h prime x0. Now we know that derivative of xk is k times xk minus 1. This is from step 2. And from step 1 we know that derivative of x is 1. So we get this is equal k times xk minus 1 plus time x plus xk, which is equal xk times k plus 1, which we wanted to prove. Then from induction we have that f prime x is equal n times x and minus 1.